Hello, everyone. Welcome to the Canadian Electricity Association's Conversation webinar series. My name is Diana Dominique, and I'm the director here at CA of the Customer Council, and I'll be your host for today's webinar. We have worked with our corporate partners to develop this conversation series, which focuses on solutions to current and future challenges faced by our industry. Today, Mr. Eduardo Gomez-Henning, who is the Director of Sales Innovation, Transmission Products and Systems at Siemens Energy North America, is here to discuss grid resiliency. The configuration and operation of the grid is evolving, and new distributed generation is being connected to the grid. User habits are changing, existing infrastructure is aging, and weather events are becoming more frequent. All of this is causing critical transmission and distribution equipment to be stressed to its limits. In this webinar, we will discuss real-life cases of how Siemens has supported utilities with the development of state-of-the-art power transformer resiliency solutions. But before we get started, we'll have time at the end of the webinar to answer any questions, so feel free to use the chat function. And we'll also send out a survey to seek your feedback on this webinar, but any other ideas that you may have on topics for future conversation series webinars. So with that, please, Eduardo, go ahead.
So, good afternoon, everyone. Thank you, Diana. So let me start. So as Diana already explained, we will be talking about grid resiliency with a focus on power transformers. And the agenda I am proposing for the discussion today is as follows. I will start with a brief description on some of the risk factors, basically why resiliency matters. Then I will explain how we in Siemens propose to tackle that resiliency challenge by using a toolbox of measures that we call PRETACT, which is the combination of prevention, protection, and reaction. Next, I will present 3 real-life cases and examples of state-of-the-art resiliency solutions we developed for users in North America, and I will be ending with some conclusions and time for Q&As. You don't need to wait till the end to make your questions. I'm more than happy to address them along the way as well. And, you know, our industry faces many challenges. The world is in transition. The configuration and operation of the grid is changing. It's evolving. New distributed generation is being connected to the grid, and habits of the users are changing as well. And power flow through that legacy transmission grid will in many cases not be anymore how it used to be. And grid and equipment may not be utilized how they were originally intended to be. So power flow will be multi-directional as well. We will have consumers that will, during different times of the day, be also producers. They are now called prosumers. We will have facilities generating and injecting power into the grid, and and those same sites could be then at different times of the day be absorbing and storing energy. Additionally, existing infrastructure is aging, and many of the components are reaching its end of life. We also have seen significant weather events are becoming more relevant and frequent. So taking all those factors into consideration, we should expect critical transmission and distribution equipment being more often stressed to its limits. And among those, special attention should be placed on power transformers. And why? Transformers are large, heavy, and sourcing of a new large power transformer is a lengthy process that usually takes 6 to 12, sometimes 14 months, depending on how specialized that unit is. The transformer then needs to be transported to the site, and on top of that, There is the installation and commissioning that can take several weeks actually, and I would say 4 weeks is an average for a large transformers. And we know the impacts of blackouts on our society can be major, starting with traffic lights and street lighting over to public transportation or communication networks. But what about the impacts on financial institutions, the industry, or, well, even healthcare facilities and hospitals? Power outages can surely be a challenge, and even more if they involve the failure of a large power transformers. But what if there was a solution out there that could help us reduce installation and commissioning time of a transformer from the standard today, which is several weeks, to only a few days? But what if additionally there was a solution so flexible that would allow us to optimize our assets by making a transformer so flexible that it could be used at several different sites? So let me share with you what we in Siemens have been doing to address those questions. And there are several factors that can affect a safe power supply. And those can be operational, like network disturbances, or load balancing situations, or incorrect operations, or just aging fleet. But they can also be weather related or natural disasters like storms or flooding or wildfires, earthquakes or geomagnetic storms. Well, and there can be other types of force outages as well, like vandalism. And there's an array of prevention, protection, and reaction measures that combined can help address those risk factors. And certainly risk exposure and needs vary significantly among different users, among different areas of our industry. And so our approach, since we started working on grid resiliency solutions several years back, has been to use a modular feature architecture. And this allows us putting together tailor-made solutions, but in line with the real needs of every individual user. And that toolbox of features helps us address holistically those risks from those prevention, protection, and reaction fields. And important to note about this toolbox is that those individual tools, those features, have previously been tested and used, meaning it's a proven and reliable technology. So let me mention some of the options for power transformers. Maybe there's a need for bullet resistance, or maybe there's a need for, well, to protect against DC currents that could drive your transformer into saturation mode, or maybe there are concerns about exposure to geomagnetically induced currents. Alternative fluids could also come into play, especially, ester fluids, maybe because the need of increased fire safety. And in a contingency situation, you might need to consider installation in an area with reduced fire clearances or reduced fire suppression capabilities. Or maybe because of environmental reasons, maybe a biodegradable fluid facilitates deployment during contingency. Or maybe there's a need for a very quick replacement, like a plug and play. As I mentioned earlier, standard installation and commissioning times are usually several weeks for large power transformers. So I will concentrate now on that portion, the reaction, and the plug and play solutions. And to do that, I will share with you 3 real-life cases of resiliency transformers developed for users in North America. So the user number 1 was a utility in the northeast of the US that reached out to us explaining the following challenge they were facing. If one of their large transformers went suddenly out of service, they would need several weeks, probably more than a month, to remove that unit, bring it out of the yard, and replace it with a new and existing spare. And it was not a matter of availability of spares or even redundancy. They had both. They could just not afford to remain in a contingency N-1 situation for so many weeks until that unit was replaced by the spare they had in their warehouse. So they needed a solution that allowed them to return to a fully normal operation in the shortest possible time. User number 2 had a very different challenge. Their fleet was aging and they did not have enough spares to cover the risk the way they wanted to. They actually could not afford to buy simultaneously all those spares for all the aging substations. So they needed a solution that ideally would be flexible enough to cover a large number of substations that had different voltage levels and that could easily be transported to faraway locations and quickly be brought into service as well. And case number 3 was to support a large and diverse fleet of generating step-up transformers. And finding a solution for generation companies is also not straightforward, as generator output voltages are generally not standardized, meaning a very diverse range of voltages would need to be covered. And here are some of the basic technical details of the resiliency transformers that were needed. So user number 1, let me move a little bit here my screen. Well, user number 1, well, he had this 300 MVA, 335 kV to 136 to 13.8. And he said, ideally, I should also be able to operate this unit in another substation with 136 to 69 to 13.8 kilovolts at a 150 MVA. He said, I definitely need an on-load tap changer for voltage regulation. I need to be it to be a fully rated transformer, not rated with full overload capability. It should be environmentally friendly as well and fire safe. The second user, well, he had really to be able to cover his needs. He said, I need at least these 5 different voltage level combinations: 345 to 230 kV, 345 to 138 kV, or 345 to 115, 230 to 138, or 230 to 115, 400 MVA. So those are large units. And on the case number 3, the challenge was, as I said, to develop a solution that would cover a very broad spectrum of low voltages from 12 kilovolt all the way to 34.5, and high voltages from 115 kilovolt to 400 kV, 240 MVA, ideally environmentally friendly and fire safe as well. And let me go this. Yeah, let me see. This is not switching. Okay, there you go. So let me now show some of the technological features just to give you an idea of all that is possible that we're used to develop those transformers. And cable connections have been available for a long time. So we said, let's use that, but let's evaluate all options and possible uses around it. And in the top of the slide, you see a conventional cable with 2 plug-in connections at both ends. But actually, that same cable can have on one of the ends a bushing with a termination, can be fitted with a bushing termination instead of the plug. And then we said, why not use that high voltage plug and attach it directly to the bottom end of a capacitive bushing? And so a plug-in high voltage bushing was born. And that means to connect both high voltage as well as low voltage sides of the transformer, you don't need to open anymore the transformer tank. You don't need to expose the active part of the transformer. So it is an all-tight socket in the transformer tank. It is pre-installed and pre-tested. You don't have to manipulate the oil. It's quick and very reliable installation. Another feature we decided to use from that toolbox of measures was using an alternative fluid instead of mineral oil. So we decided to use synthetic ester, which has two key advantages over mineral oil. The first and most important one is that it offers enhanced fire safety. The second one is that it is environmentally friendly. And on the left-hand side of the graph, you see that the fire and flash points of ester fluids are much higher than the ones for mineral oils. That means the likelihood of igniting is much lower than in the mineral oil case. Additionally, esters have a lower gas generation rate, a gas conversion rate, which means that in case of an arc flash happens inside of the transformer tank, they produce less amount of gas bubbles than mineral oil, and so the explosion risk is also lower. And esters, I mentioned, are environmentally friendly. And what does environmentally friendly mean? I think the best way to measure that is biodegradation. And you see in this chart on the right-hand side, the time of days it takes to biodegrade. And you see the line at the bottom on the x-axis, there's silicon. So silicon fluid doesn't biodegrade at all. And then we see mineral oil biodegrading less than 10% after 30 days. But esters, both natural and synthetic esters, they biodegrade close to 90% after only 30 days. So this is the key topic here, measuring the biodegradation in time, in days. And there are some standards and guidelines on how to do that. That's OECD and in IEC 61039. So let's look at the outcome for user one. And in the picture you see the 300 MVA transformers that connected together deliver a 300 MVA power. The transformers, and maybe you don't want to read the whole thing, it's very small letters, but you can look at the slides afterwards. The transformers have two operation modes, the 345 kV and the 136 kV. The transformers have a load tap changer voltage regulation. They have a de-energized switch to change between operating voltages. On the high voltage side, we have plug-in bushings. And on the low voltage side, and low voltage in this case is 136 kilovolts, this transformer was designed to have two options, either a plug-in bushing or a plug-in cable. For the neutral and the tertiary, we also used plug-in cable. The insulating fluid was synthetic ester, Midel 7131. And the solid insulation, for that we use Nomex and thermally upgraded paper. And we also developed a control cabinet with heavy duty plug quick release multi-connectors. So at the end, we were able to design and develop this compact unit. You see the weights there for a unit of this size is that it's lightweight. It's 60 tons without oil, 98 tons fully assembled and with oil. That has enhanced fire safety, biodegradable fluid, and benchmark assembly and commissioning times. And I will say some more words about that a little bit after. User number 2 was this one, and you see there the 3 transformers that are now finished and they were ready for shipment. Extremely flexible as well, and the 5 different voltage levels could be achieved. Also had a tertiary winding. On the high voltage side, we had plug-in bushings, and all the low voltage, which are 138 and 115, we had both plug-in cables or plug-in bushings for that added flexibility. Neutrals and tertiary, again, with plug-in cables. This transformer was with mineral oil and also had a common control cabinet for that. This one really extremely lightweight, 50 tons without oil, 75 tons with oil, meaning it can be transported with oil, and really serve the purpose to optimize the spare fleet. And now here, user number 3, and I mentioned generator step-up transformers and the challenge of having a lot of different voltage levels that need to be covered if you really want to cover a large fleet of generating units. And the solution here with that one, we were able at the end to find 41 different voltage levels combinations in the low voltage from 12 all the way to 34.5, and on the high from 115 to 400 kV. Extremely lightweight with enhanced fire safety and using biodegradable fluid as well. Digitalizing your equipment is also important, and you should consider it when selecting your high voltage grid equipment. And the advantages are some of those are like real-time asset status, automatic messages in case of alarms, and most importantly, you can have enhanced asset management possibilities. Digital twin and AI technology is available to aid you in deciding how to make best but safe and reliable use of your equipment. It can help you calculate a life and use of life and life expectancy. You can make real-time assessment and projection of the impact associated with overloading, which might be a useful feature during contingency operations. So our proposal is using, for example, a cell phone network to connect to the cloud. And then, accessing and processing of that information in the cloud can be done through very secure, but at the same time, user-friendly interfaces. Administration becomes simple as well, and you do not have to deal with complexities of trying to expand and manage your own IT infrastructure for such tasks. And one might think, who needs digitalization now? But think about it. A power transformer is expected to live 30, 40 or more years. So the proposal here is, even if you think you do not need that level of digitalization immediately, still consider building in the right provisions to make sure your equipment is fit for the future. And important, of course, be sure to select a secure but easy to use ecosystem with a scalable open architecture. How does real life look like? And I want to share with you how the deployment of these different transformers looked in real life. And by the way, user number 1 was Connect, New York. They decided they wanted to make a real life drill to test the new resiliency solution. It started with a simple sketch assuming a failed transformer had to be bypassed. And you see there in the middle the failed large unit, and around it the resiliency units. But then it went on, and we said we have to use the real substation layout drawings. And here you see the transformer that needs bypassing in the middle. On the left hand, you have the 335 kV bus bars. On the right hand, the 136 kV base. And then it was a matter of finding the best placement for those resiliency units. And one of the nice things of having the combination of cables and bushings is that you can rotate your transformers in many ways and put them in places that normally you wouldn't be able to. So this is the final arrangement that was decided by Con Ed. You see on the left the three resiliency units, and you see the high voltage bushings are installed, but the low voltage it's with cables. And you see the cables running around the unit that needed bypassing. And then the cables go to a structure that was also developed for low voltage pod heads to connect the 138 kV bus bar. And here some picture as well. The first picture, you see the transformer being lifted with a crane, and that transformer was actually transported from the warehouse to the substation ester filled. It was liquid filled. So we saved their time by avoiding to have to fill the transformer on the pad. And since the transformer had the plug-in bushings, and the inner socket was already pre-wired, you didn't have to open the transformer anymore. You didn't have to expose it. You didn't have to lower the oil even. You just took the plug-in bushing and connected it. On these slides here, we see here the installation of the 138 kV, that's a low voltage, as well as the tertiary cables, the 13.8 kilovolt cables. And you see there a technician preparing the plug-in connector, is cleaning it. That's all that needs to be done. But on the right-hand side, you see when the cables are already plugged in the transformer itself. And this is a picture, a bird's view picture of the substation with the three resiliency transformers connected. And you can actually see the red cables. If you look close, they are building the delta, and the black cables, they are running past to the right-hand side with the 138 kV connection to the 138 kV bus bar. But what was the result of the demonstration? So Con Ed was extremely satisfied with what they were able to achieve, definitely benchmark assembly and commissioning times. From the start of the process, and that included bringing the resiliency units from the warehouse to the substation, to installation of the bushings, installation of the cables, wiring of the protection and control cables, to full loading, energization, and immediate full loading of the transformers, less than 3 days. So this is really benchmark. And we said before, normally this process takes 4 weeks. And additionally, this was not a real emergency, it was a drill. So the crews, they were not asked to work at night, but only during daylight hours. There was no need for that. the actual work time to get all of this done was actually only 30 hours. Meaning, in a real emergency situation, you could think that you should be able to do it in less than 3 days, actually. The second user was Westar, also in the US. And I visited their warehouse, I visited their substation about 2 years ago. And what really impressed me the most was the detailed planning they had done to really be prepared for the unexpected. They had very detailed contingency deployment procedures that documented every single step of the process to deploy the resiliency transformers. They had numbered and marked site-specific containers as well. That meant in the case of a contingency, they would just pull out the procedures. The procedures would tell them for X substation which of the containers were the ones that needed to be shipped. They didn't need to check them anymore. Everything was in the containers, including the tools they were going to use for that deployment. And here a picture of the units already deployed. And on the left-hand side, you see the 3 single-phase transformers. And you see they are rotated as well. 2 of them have the conservator on the left. The other one on the right has the conservator on the right. So that was just enable the better placement of them. You see there as well this centralizing cabinet for the protection and control signals. This is a really compact unit, as I mentioned before. And on the picture on the right-hand side, you see compared to technicians sitting there or standing there by the unit, that it's really, really small. So it really served the purpose. First on the CapEx. And you know, I started discussing with another user some time back, why not use your resiliency transformer for one more thing, and that would be to enable better utilization of existing assets. And the standard procedure when a transformer is believed to be reaching its end of life is to start procurement of a replacement unit, of course. And once that new unit is available on site, you have 2 options. You retire and scrap your old equipment and replace it with a new one. But are you sure that old equipment was really at the end of its life? It was working, it was energized. Maybe it had an additional year of life or 2, or maybe 5, or maybe more. So maybe you missed the opportunity to continue using it before doing that spending on the new equipment. The other option is that when the new equipment arrives to the site, you decide to store that replacement until that old one fails. And maybe then you store it for 1, 2, or 5 years, meaning you invested in an asset that you're not using. So why not consider instead running that old transformer until it effectively stops working, having, however, peace of mind that you have an available resiliency transformer that you can very quickly deploy to replace that failed unit. And only at that time you would need to purchase that replacement transformer. You wouldn't need to purchase it ahead of time, but only when you need it. So you would ultimately be better utilizing your existing assets. You would be delaying your spending needs, and that would surely have a positive impact on your finances. And with that, we're coming to the end of the main slides. So let me do a wrap up of what I shared today. So first of all, it is clear that needs vary significantly among users. The good thing is there are safe, sustainable, and proven technologies available to address those individual needs. Resiliency solutions can definitely help reduce your capital expenditures, and we have seen users optimize their spare fleet spending with them. But resiliency solutions can also help as well reduce your operational expenditures, and for example, reducing installation times from several weeks to only a few days, or by reducing spending on emergency generation and fuel costs. Also by using them not only during contingencies, but during planned outages. And in those cases, you can have reduced rental costs or avoidance of expediting costs, for example. I also explained how resiliency solutions can as well enable better utilization of existing assets. Digitalization is a good idea. Digital twin and AI can help optimize your asset management. So make sure your new equipment is fit for the future. To successfully utilize your resiliency technology, make sure you develop very detailed contingency deployment procedures and conduct as well drills to test and upgrade those procedures. And be aware, a resilience grid is what is expected by the end users. And users are more and more electricity dependent, and they will only be more dependent a few years from now, which makes them more vulnerable as well and less tolerant to outages. And finally, whenever possible, take advantage of existing sustainable technologies. With them, you can enhance protection of the environment and will also additionally better safeguard your image and reputation. So with that, I reached the end of the presentation. You will have afterwards access to the slides. And this slide, you have my contact details. You have a link where you will find additional information on resiliency, as well as references to some white papers. So I'm guessing we come now to the Q&A section. So Diana.
Hi, thank you, Eduardo. That was very fascinating. And for participants who are joining in the webinar, feel free to add your questions into the chat function. And in the meantime, I thought a lot of very interesting points that you raised, and your first user case with Con Ed. I mean, 3 days compared to 4 weeks. I found that truly amazing. And what would you say additional considerations that our member utilities have to take into account when they're implementing this type of technology, quick deployment technology?
Sure. I would emphasize on the importance of detailed deployment plans. And I mentioned some of the things that Wester did, but there were other things as well, like evaluate your road conditions to your substations, maybe do a road survey, get in contact with your truck hauling companies and agree upfront with them on which equipment should be used for a seamless deployment. And you will need to ship not only the transformers, but as well the bushings, the cables, and the tools. So the plan should as well, for example, define on the order that each of the trucks should enter the warehouse to load the equipment and the transformers, as well as the order the trucks should arrive at the substation to unload it. And believe me, you could literally lose many hours if those are not deployed in an optimized order. You could have a traffic jam in a small countryside road if you have all of the equipment trying to get into the substation.
So really think about the logistics around the deployment?
Correct.
Okay.
So that's just really looking very deeply into the logistics and documenting them, have them written and available so that the moment you need them, they are all predefined and ready to go.
Okay, thank you. And in your conclusion also, you had mentioned, and throughout your presentation, there was quite a lot of emphasis around sustainable technologies. So what would you feel are the advantages and limitations of using biodegradable fluids in these high voltage transformers?
Sure. And I already mentioned some of the advantages like increased fire safety and increased explosion withstand on top of that they are environmentally friendly. But other advantages are their ability to reduce the speed of aging of the solid insulation of the transformer. And why is that? Water degrades the cellulose, that's the solid insulation inside the transformer. Water breaks the long cellulose chains, so it reduces the polymerization degree. But esters have the ability to absorb, to extract the water out of the solid cellulose, slowing so down the degradation process. Some limitations, well, there are two types of esters, natural and synthetic. And at low ambient temperatures, let's say -20°C, natural esters solidify. So the recommendation is using instead synthetic esters in cold climates. Natural esters also oxidize when in contact with air. So unless you have a seal system, the recommendation as well is to use synthetic ester instead of natural esters. Maybe also to consider, you might need to train your crews on the new type of fluid. You might need to train your oil lab technicians, if you have, to learn how to evaluate, for example, dissolved gas analysis results on ester field transformers. You should probably consider as well upgrading your installation and assembly guidelines for the new fluid.
Great, thank you, Eduardo. And did you have any feedback from the users on how they're using these units?
Sure, and there was, we got an additional feedback. Some of the users reported they had plans to use them to bypass transformers during planned outages. So not only during contingency, during emergencies, not only when a transformer failed, but during a planned outage, for example, to conduct a major service work on older equipment. And having the possibility to use this easy to install quick deployment technology with the combinations of bushings or cables and install it actually far away from the unit that you need to service opens for them a whole new spectrum of servicing possibilities that in the past was just not available.
So additional positive benefits aside from those that you mentioned about flexibility and addressing aging infrastructure, timing and deployment, I guess that would fall under supporting a diversified fleet, or you mentioned extending life of assets as well. So there's all these positive benefits that you had mentioned, and so a few more that you've received from people who are your users who are actually have deployed this technology.
Definitely, and users, and I say every user has a different need, but only when those users have the equipment and I thought they had thought about it and they started, well, we started very deep discussions on the engineering side and how the transformer should look like and what features they should have. They started thinking immediately on additional possibilities all that new technology would offer them. Yeah.
Well, thank you, Eduardo. Really appreciate your time today and talking to us about this Siemens quick deployment technology and addressing grid resiliency. And for members who are on the line, to let you know that all of our future events and webinars can be found in our monthly newsletter, The Current Affairs. And you can also go to our news and events section of our website at electricity.ca. And this recording will also be uploaded to the library section on our website as well. So I wanted to wish Eduardo a good day, and everybody else as well. Have a great day.
Thank you, Diana. Stay safe, everyone.
Thank you. Bye.
Bye.